Scheduling systems are very important in this modern age. Whether if you're a student, or if you're a worker, or perhaps if you're just a really busy person. In this modern age, of course, companies are in constant competition with each other, knowing in this very, very demanding age. Sometimes companies meet, let's say, power downs, maybe malfunctions, or perhaps absent employees. Given these, sometimes it's difficult for small companies or small factories to delegate tasks, which is important, where should I go next. This halts progress and, of course, wastes a lot of time. According to SDG 8, based on the workforce, and specifically on 8.2, we plan to innovate machines that could help the workplace to solve this dilemma. Using discrete math applications, we will use comb sort and, of course, Dijkstra's shortest path algorithm.
For the time complexity of this system, it integrates two algorithms, which are COMSORT and Dijkstra's algorithm, that both are being used together to create a priority list that can determine the order of tasks that must be accomplished first, while finding the shortest path possible to a certain workstation so that an employee can work on said task. We will first analyze the two algorithms in terms of their own individual complexity before summing it all up together. Starting with COMSORT. As mentioned previously, COMSORT is a better version of bubble sort, with having an improved average time complexity of n squared divided by 2p, with p representing the number of gaps that will go through, and n representing the number of tasks. Next, for Dijkstra's algorithm. To differentiate the values of the two algorithms and avoid any further confusion, we'll use V to represent the number of workstation. Since Dijkstra's algorithm takes its time to go through each possible path to find the shortest path, this gives the time complexity of V squared. Now, after going through all their time complexities and understanding how each of them work, we can now piece the two of them together by going through the process of our program. So, it starts with the Dijkstra's algorithm to determine the best and shortest path to reach a specific task. So, understanding this portion of the process, we can say that it will cause an initial big O of n times v squared, which is then followed by COMSORT that will set these tasks in proper order. So, depending on the list arrangement, we could get different equations. But for this version, we will be focusing on its average case, which is mentioned being n squared divided by 2 raised to p. This leaves the overall average time complexity of n squared divided by 2 raised to p plus, as previously mentioned, nb squared. This equation itself can still be changed depending on whatever list the input was given. This can accommodate both best case scenario and worst case scenario of COMSORT, and it's very easy to change the equation from the one that I mentioned earlier by changing the first part of the equation of n squared divided by 2 raised to p with the appropriate time complexity of COMSORT.
Now, to further define, what is comb sort? As we may all have known, bubble sort has a time complexity of n squared. Now, bubble sort compares from start to finish as it compares element to the elements beside it. It compares if the element is bigger than the other element. If so, they interchange. If the left side is small to begin with, no change occurs. And given to this, it is kind of slow. Comb sort, on the other hand, uses this so-called gap. This gap starts with the array length and is divided by 1.33 as it progresses and compares each time. The more that the gap shortens, the more that the array is sorted. Now with this, the good thing about comb sort is that it removes so-called turtles, or in other words, small values at the end of the array that bubble sort cannot solve. Using comb sort, we will use this to identify which tasks are most important in the fastest way possible, which task is more important for the worker to do, and what is needed as a priority. Next, you have Dijkstra's shortest path algorithm. Now with this, we have a weighted graph syncing point to point. To further define the need for this, normally in a workplace, functions, utilities, rooms, or perhaps machines for the said factory or workplace are not in the same place altogether. Sometimes they can be far, they can be near. In the workplace, we want to maximize time and we want the shortest path to go to point A through point B with the least effort. Using this weight graph, we use Dijkstra's shortest path algorithm for the workers to go to the shortest path that they can go. Whether they're lifting very heavy things, they will require more effort given this algorithm.
This is the flow of our production scheduling algorithm. The first step of the program is to load the task list from the file that's called task.txt. Each task includes a unique ID, its urgency level, deadline, required machine time, and the target workstation, where the task must be completed. So for example, our sample input contains 4 tasks. The program reads each line and creates a task object in memory. This ensures all necessary task attributes are stored and accessible for subsequent scheduling. Once the tasks are loaded, the program calculates a priority score for each task. Priority is determined using a weighted formula that considers urgency, deadline, and machine time. In our implementation, this is the formula. Priority equals to the urgency multiplied by 3 plus 100 subtracted from the deadline plus machine time multiplied by 2. This formula gives higher priority to the tasks that are more urgent, have shorter deadlines, or require longer machine processing time. The priority values will guide the scheduling sorter in the next step. So for our sample task, this computation results in priorities ranging from 104 to 128. This ensures that the program will process the most critical tasks first. After computing priorities, the program sorts the task list in descending order using comb sort. The result in the task list where the highest priority comes first. In our sample, the sorted order is T4, T2, T1, and T3. Next, the program loads the factory layout from a file named workstationgraph.txt. This file contains the adjacency matrix representing distances between workstations. So for each row and each column corresponding to a workstation, and then the matrix entries indicate that a travel distance between them. So a 0 indicates that there's no direct path between 2 workstations. Then, the program iterates through the sorted task list to determine the optimal path for moving between workstations. So, for each task, Dijkstra's algorithm is applied to compute the shortest distance from the current workstation to the task's target workstation. So, for our sample input, this will be the path. Finally, the program outputs the optimized schedule to a file named schedule.txt. So the file contains 2 main sections. So first of all, it's the optimized route for each task and the sorted task order with their computed priorities. This allows the factory staff to follow the planned sequence of tasks and the most efficient path between workstations. This reduces worker fatigue and also, I guess, improves workflow efficiency pretty much. So basically, the program flow can be followed in these 6 steps. So first of all, load tasks from task.txt, compute priority scores based on urgency, deadline, and machine time, sort tasks in descending priority using comb sort, Load the factory layout from workstation graph.txt. For each task, compute the shortest path using the Dijkstra's algorithm. Then output the optimized schedule to schedule.txt.